Things of the day. I, Asha K, Assistant Professor, Department of Electronics and Communication Engineering, Sai Vidya Institute of Technology, going to present in today's class Analog Electronic Circuits. Module 1, we have transistor biasing and stabilization. In that, we're going to learn in today's class fixed bias circuit design and analysis. Let us now discuss about the analysis and design of fixed bias circuit. Here we have a question like derive the necessary base bias or fixed bias circuit of a transistor, obtain the expression for the stability factor S beta, SICO and SVBE, and also draw the necessary circuit diagram. Let us now discuss about the fixed bias circuit analysis and design. The figure 1 shows the fixed bias circuit. It consists of coupling capacitors Ci and Co and one base resistance Rb and another one collector resistance Rc, a power supply plus VCC and a transistor, an NPN transistor is used here. Now we will analyze the DC analysis of fixed bias circuit by open circuiting the coupling capacitors and also removing the AC input applied to the fixed bias circuit. The DC equivalent circuit is shown in figure 2. It consists of plus VCC, RB resistance, RC resistance and a transistor. Let us now analyze the DC analysis of fixed bias circuit. It refers to analyzing the circuit so as to establish the operating point or Q point in the absence of an AC signal. For DC analysis, what we do here it is Ci and Co will be open circuited and AC source is made 0. So, we will consider the DC equivalent circuit of fixed bias circuit. Then to find the input current IB, we apply the Kirchhoff's voltage law to the input side of the circuit. By applying KVL, we are going to get negative to positive plus VCC, then positive to negative minus IBRB, positive to negative, base to emitter voltage minus VBE is equal to 0. Then we'll rearrange the terms. VCC minus VBE is equal to IBRB. Then the current, input current IB is equal to VCC minus VBE divided by RB. We call this as equation number 1. Now to find the output current IC, that is the collector current, we know that IC is equal to beta times IB, where beta is the ratio of output current IC by input current IB. It is called as common emitter current gain. Then to find the output voltage VCE, we apply the Kirchhoff's voltage law to the output side of the circuit. If we apply the KVL to the output side of the circuit, we are going to get, see this is the circuit which consists of RB resistance, RC resistance and a transistor and a supply. The voltage across the collector and emitter is VCE. The current flowing through RC is IC. By applying KVL to the output side, here negative to positive plus VCC, then positive to negative minus ICRC, positive to negative minus VCE is equal to 0. Then after rearranging, we are going to get VCE is equal to VCC minus ICRC. Then the important equation you have to remember here are VBE is equal to VB minus VE, base terminal voltage minus the emitter terminal voltage. Then VCE is equal to collector terminal voltage minus the emitter terminal voltage, and the operating point, that is the output current ICQ, is given by beta times VCC minus VB divided by RB, and VCEQ is given by VCC minus ICQ into RC. To draw the DC load line, consider the output side of the equation, that is output voltage equation, that is VCE is equal to VCC minus ICRC. To draw the DC load line, what we do, we are going to substitute the output current IC is equal to 0 in equation 1. Then we are going to get VCE, the output voltage, is equal to VCC for IC is equal to 0. We call it as point A VCC comma 0. This is nothing but x-axis value and the y-axis value. This value appears on the horizontal axis of the output characteristics curve. Similarly, we are going to substitute VCE is equal to 0 in equation 1. What we are going to get here, the output current, that is equal to VCC by RC for constant, that VCE is equal to 0. We call this as equation point B on the output characteristics curve 0, VCC by RC. It appears on the vertical axis of the output characteristics curve. Here the Q point values, we know that x-axis is output voltage, y-axis is the output current. Now draw the output characteristics curve for a transistor for fixed bias configuration. The variation of the output current IC with respect to output voltage VCE for constant value of the base current IB1, IB2, IB3, etc. The output characteristics curve is shown here. For this particular curve, we have the one point that is on the vertical axis, that is x-axis is 0, the y-axis is VCC by RC. We have the another point on the horizontal line, we call this as VCC, 0. When we join these 2 points, we are going to get a line. That particular line is called as DC load line. Now we are going to understand the variation of the Q point or the operating point with respect to different parameters. The Q point upon the DC load line, a point, the VCEQ value and ICEQ value are joined. Now we will analyze the variation of the operating point with respect to base current IB. If base current is going to vary, say for example for 20 microamperes, 30 microamperes and 40 microamperes, we are going to get the 3 different Q point or the operating point. Now by varying the collector current, that is the output current, we are able to get the 3 different operating points on the output characteristics curve. Similarly, with the variation of the supply voltage VCC, also we will be able to get the different operating point. The images here shows the variation of the operating point with respect to the input current, the output current and also the supply voltage. As observed in the previous slide, even though it is the simpler circuit, however, it offers worst stability against the variation in the temperature or the transistor gain as compared to the other configurations. It is therefore prone to thermal runaway and it is rarely used configuration. We discuss the stability factor. Here, stability factor with respect to leakage current ICO. SICO, it is the rate of change of collector current with respect to the leakage current. The collector current IC is expressed in terms of the base current IB for common emitter configuration as in this particular equation. That is, IC is equal to beta times IB plus beta plus 1 into ICO, where IC is the collector current, beta is the current gain, IB is the base current, and ICO is the leakage current. Differentiating the collector current with respect to the leakage current, keeping the transistor gain and the base emitter voltage as constant, we are going to get the SICO stability factor. That is, differentiating this particular equation star with respect to ICO, delta IC by delta ICO is equal to, since this term is constant, we are going to get 0 here, then ICO with respect to ICO differentiation is 1 and we'll be remaining with beta plus 1. Hence, stability factor for fixed bias configuration with respect to the leakage current ICO is given by SICO is equal to 1 plus beta. The second stability factor that we have here is SVBE. It is defined as the ratio of change in the collector current with respect to change in the base emitter voltage. That is delta IC by delta VBE for constant leakage current and the gain. Now, the expression for collector current is given by IC is equal to beta IB plus 1 plus beta times ICO. For fixed bias circuit, the base current is given by IB is equal to VCC minus VBE divided by RB. We are going to substitute equation 2 in equation 1. After substitution, we are going to get IC is equal to beta into VCC minus VBE by RB plus 1 plus beta times ICO. Differentiating the equation 3 with respect to VBE, keeping ICO and beta constant, we are going to get the delta IC by delta VBE is equal to minus beta divided by RB. Since we have here ICO and beta constant, this gives us 0, and when we are differentiating IC with respect to VBE, we'll be going to get minus beta with this term by RB into delta VBE by delta VBE, that will be equal to 1. Hence, the stability factor SVBE is equal to minus beta divided by RB. Now, we will discuss about the stability factor S beta. The stability factor S beta, it is defined as the ratio of change in the collector current with respect to change in the transistor gain, keeping both the saturation current and the base to emitter voltage constant. It is written as SB is beta is equal to delta IC divided by delta beta for VBE and ICO is equal to constant. The expression for fixed bias collector current is given by IC is equal to beta times IB plus beta plus 1 into ICO, where IC is collector current, beta is the current gain, IB is the base current, and ICO is the leakage or saturation current. If ICO is very small compared to the base current, then we can write IC is equal to beta times IB. Then substituting beta is equal to beta 1, we are going to get IC1 is equal to beta 1 into IB. Similarly, by substituting beta is equal to beta 2, we are going to get IC2 is equal to beta 2 into IB. Then subtracting equation 1 from equation 2 will give us IC2 minus IC1 is equal to beta 2 minus beta 1 into IB. Delta IC is equal to delta beta into IB. Then IB is equal to delta IC by delta beta is equal to IC1 by beta 1. Similarly, IC2 by beta 2. Hence, the stability factor S beta is nothing but IC1 by beta 1. So this ends the stability factor S beta. So in summary, in this particular presentation, what we have learnt is fixed bias configuration, the base current, collector current and the output voltage VCE, also the three stability factor SICO, S beta and SVBE. Thank you one and all.